Hello everybody, this is David. Welcome to part 5 of the 7-step processor series. By the end of part 4, 3 main components of the processor had been described and verified using Verilog: the main memory, the ALU, and the control unit. So the next thing that needed to be done was to write descriptions for the remaining smaller components of the processor, and then put all those modules together into one processor description. For the processor description, I/O ports needed also to be taken into consideration, and so that's what I did. I wrote those remaining modules, put them together into one processor module. Then I developed test circuitry for verifying the processor. And I was having some trouble testing the circuit, and I wasn't sure about how I was using the tri-state buses and out, so I reached out to my old university professor, the one who introduced me to Verilog, and this is what he had to say about tri-state buses. They're tricky, they're slow, they don't implement well, there are many ways to break them, and then many Verilog programmers will design away from tri-state even at the cost of multiple directional buses and data selectors. And that's so you can see how fast they can push the design, because tri-state buses are slow. So I ditched the tri-state design for the data address bus and replaced it with a circuit that will route data to and from different components that have different connections. And here is what I call CPU-B. The last one with the tri-states was CPU-A, this is CPU-B. And you'll notice the GPR file. I'll get more into these as I go. I'll explain all of these. You'll understand what's going on, I promise. But the GPR file is where all 4 of the registers reside now, so that I could have one input and output communicating with this data bus that has an input and output to a lot of the components, some inputs from some, and some outputs to some that don't have outputs back to the data bus. And then there's the new I/O, which is the interface that to the processor from other modules in the system. And so here's really some summary of changes for just going from the tri-state model from the book to CPU-B. So all the in-out ports have been replaced with separate input and out ports, and that only affects these 3 modules. If you look at the diagram, for the GPRs, each general purpose register, the IAR and the RAM has an in-out port. Everything else just has an input and an output. Remove bus 0, it's no longer needed based on the data bus design. Will drive all zeros as a default value when not routing data to the component. Well, to ALU-A specifically in this case, because that's what bus 0 was created to provide a 0 for clearing the flags. Well, now there will be a 0 there from the data bus, so we don't need a bus 0. Added a register file module to encompass all GPRs. I talked about that. Added the data bus module to route data, and the control signals for that is based on the step, which is now an output from the control unit, some bits of the instruction and flags. This will all be explained shortly. Added an input-output module, you saw that. Added outputs from the control unit, like I just said, I'll show you in a second. So really the only changes from modules that have been completed already include changing the RAM from having an in-out port to now having input and output ports, and then adjusting the logic for that purpose. Like I said, the control unit, the step is now being output. It's not just an internal wire for the purpose of the data bus module control signals. Excuse me, and added an output wire for signaling a flag that has been detected during the jump if instruction, right? Jump one of the flags. Also, bus 0 has been removed, and I fixed an I/O operation. Here's a summary of the control unit changes again. Bus 0 is removed, stepper is now an output. That flags detected signal is simply from OR gate OB, because it's one of the flags that gets detected, right, coming from the flags register. And then I went ahead and replaced the AND gate A21 and NOT gate N3 with a NAND gate I call NA1. And now let's get into the registers. Here's the ACC register, which is a register. You can see it down here in the bottom left, right? It has an input of 8 bits, an output of 8 bits, a set, and an enable signal. Here's the Verilog code for it, and here's the simulation results. and you can see that when set comes in over here, the value that is at the data in gets set into the data reg, and when enable goes high, that value is outputted. Here's bus 1 module. This is the gate schematic for it, but I just simply did it with an assign using a multiplexer. So when that bus 1 signal comes in, which is E_B1 here, and you can see in the simulation that the output will be 1, which is what we want, right, for clearing the flags. And so here's the flag module. It's just half a byte essentially. It's not really a register, it's the byte, right? It only has the set and not the enable. So whatever the input is, when that S signal comes in, it propagates to the output. And you can see that over here in the simulation results. And here's the code for it. Here's the IAR module. Now this is a register, but it also has a reset that I added to it for the purpose of keeping it at address 0, which is the start of our address space for instructions. Right, the reset also holds the stepper at step 1, right? So you're essentially, when you put at reset, you're putting the CPU to start over. And you can see how in the simulation, everything's working correctly. Here's the IR module, which is simply a byte, just has the set. Every time the set signal comes in, what's at the input propagates to the output. TMP module is the exact same type of module, just a byte. Okay, at this point, now we have covered all of the modules except for these 3 new ones, which I'll cover right now. First, we'll go over the GPR file, which it's a register file. It's holding the 4 registers, R0 through R3. It has 1 input and 1 output tuned from the data bus module. All the set and enable signals from the control unit go into this GPR file and still control all of the registers. So for the data bus, from the data bus module, whatever the input will be driven to this GPR file, and that input will set at each of the 4 registers. But the one that the data gets set into is when the set signal comes high from the control unit. And as far as the enable goes, when it's outputted, it's the enable signal from the control unit that outputs it to the data bus module. Here's the code for one of the registers here on the left, and then just instantiating 4 of those, including them into the GPR file module. All these inputs are all the sets, all the enables, the data in and the data out. You can see by the simulation results that okay, the data in, it changes its so 1 is getting set into R0, 5 into R1, AAR2, FFR3, and then when the enable signals come along, you can see the data that was put into it comes out of it. Next, we'll cover the IO module. It's like any other register module. It has data coming to it, a data bus into it, and a data bus out. And this is the data that goes to and from a GPR register for IO operations. Data coming into the CPU comes into a GPR register, and data going out during an IO operation comes from a GPR register. And the signal that controls the routing of the data pretty much through the IO module from CPU out onto other system module, or from another system module to the CPU. That signal is the IO input output signal. Pretty much IO clock E, IO clock S, and IO data and address are just the same signals coming out. They're just renamed. Also instruction, the first 4 bits of the instruction, because this will be reading IO input output, will be a 0 because there's a gate there now, and wanted to make sure that it's only the IO modules only being activated during the IO instruction, which is 4 bits of binary 0, 1, 1, 1. Here's the code for it. It's split up between, here's the port declarations over here, and then all the logic on the right. You can see it's just all the signals from the previous slide. The logic for it is so this was kind of tricky, but not really, because it has the in out, and then it also has an output. So the input is CPU out, so the input to the IO module is what's going out of the CPU, And what's coming into the CPU is the output from the I/O module back to the CPU GPR. And then there's the in-out signal that is the interface between the CPU and other system modules. And you can see in the simulation, okay, right here where the arrow is, right? So we're enabling the input, which means, and then look at the top wire here, it's a 0, so it means it's an input. Data and address is not real important right now because we're not really communicating with another device. This signal right here, mod data, is simulated data coming from another device, and that's hex 55. So when we're enabling the input, we want to input to the CPU, that means we're getting hex 55 coming from another system element, and then so CPU in becomes 55, and then the 55 is also on the in out. It's an input at this point, and that data is going all the way through into a GPR. Now on the other hand, for an output operation, right here, we will set the output. You can see the top signal here is 1, so it means it's an output. We're enabling, or we're setting the output, and so the output that we are taking, so CPU out, so the GPR register is driving 1-1 into the I/O module, and then that's being driven out of the in-out. It's now an output is 1-1 during an output operation. And these other two just do the exact same thing with different sets of data. So we can see the I/O module is working good. Now let's cover the data bus. So these on the left here we have the from. These are the portions, the components of the CPU that have outputs, and all those outputs go into the data bus. And now all the portions that have inputs, the data bus is driving 8 bits to each one of these. And then how the data is routed from a device or a component to another component is based on these routing signals. And we're looking at the instruction, the first 4 bits of the instruction, the step, because based on the step, different signals need to route, and we'll look at all those here in a minute. And then also instruction 4, which is simply for I/O operations, because that 5th bit of the instruction determines whether it's an input or output, and then that flag's detected, which is OR gate OB from the control unit. Those are all the control signals for the data bus. Oh, this is a drawing I did just to show you how I kind of came up with the logic that you're about to see in the Verilog code. It's going to look real confusing, but this is the drawing I came up with to design the data bus. Here's all the control signals and when they're supposed to activate. And so basically this is how I know that it's the step and the operation that controls the data. And here is the data bus module. It's simply a combinational circuit. There's no registers or Verilog regs in here. It's all inputs are driving the outputs based on input control signals. So this is all multiplex logic right here, and all of this logic right here came from this information right here, when to route, like for instance step 1, right? We're going to go to the memory address register and ALUA from the IAR. We'll see all this in the simulation coming up right here. So here it is, step 1, right? Every operation, every instruction, step 1 is the same. It's part of the fetch, step 1, 2, and 3. So I'll only cover step 1, 2, and 3 once. And so here's step 1. What do we have? We have the instruction address register is enabled to ALUA so that bus 1 can be enabled and add 1 to the address in the instruction address register and gets set into the ACC. And it's also sent to the memory address register to address RAM for the current instruction. So this is correct. Step 2, then we take the instruction from RAM and put it into the IR. So how you know this works, right? You can see, let me go back. You can see the I up here. These are actually the from, and these are the to. So from IAR, we have a data of 5.5, and you can see in this first column here, 5.5 shows up at ALUA, and it also shows up at the MAR, memory address register. And then in this case, we have RAM to IR. The data that's simulated for RAM is hex AA, and you can see that it's actually being routed and inputted to IR. is AA here, and then step 3, the ACC, which is the address plus 1, which is hex 11, is being presented back to the instruction address register for the next instruction. And so now the simulation goes through each one. I went through each one to make sure each one works, but I'll just kind of flip through these. But you can see for each one, the arrow is pointing to the step, and so for each one now it'll be step 4, 5, and 6. And for the add instruction, we have general purpose register B to TMP, and then register A to ALUA, and then we take the result from the ACC and put it back into register B. Same thing for an AND instruction, does the exact same thing. The shift right instruction, which, remember, these control signals are still activated, although this is a one operand instruction. It doesn't hurt or do anything that register B is being used, because when it comes to the actual operation, the ALU will only look at the value at ALUA for register A, and then we'll put that back into register B. The compare operation does two things, and then it compares, right? It loads from register B, then register A, and then it sets flags. So there's no step 6 operation. Okay, that's all the ALU instructions I wanted to cover. They work. So now we go into a load instruction. We go from reg A. This is where we are loading a value from a register B into RAM at the register and register, or the address in register A. I know, it sounds confusing, but that's what happened. Register A is the address, and then we enable RAM to go into register B. Step 6, we do nothing. The store instruction does the opposite. We're going to do step 4 is going to be exactly the same. There's an address in register A that we want to set to the memory address register, and we want to enable reg B to be stored into RAM. Step 6, do nothing. The data instruction does the same thing as step 1. It sets the value from the instruction address register at ALUA and the memory address register. Then we take the value from RAM and put it into reg B. Then we take the ACC and put that back into the IAR for the next instruction. We have a jump register, which has one operation. We're going to take register B and present it to and set it into the instruction address register. And then nothing for 5 and 6. Jump instruction, step 4, 5, step 6, do nothing. Here's the like a jump if. I call it jump if, but it's actually jump. You put CAEZ, combination of the letters that you want to test for. And you can see that the very top signal in the simulation is flags detected. So in this case, there will be no flag detected, so a step 6 will not happen. We're going to set up to jump, but then there's no step 6. And then in this case, the top signal flag is detected. So we'll do the same setup as the previous. We'll set up to jump, and then for step 6, we'll actually jump by taking the address from RAM and putting it in the instruction address register. The last operation is the IO instruction. This has the IR_IO signal, which signifies it's an input operation. If it's a 0, we're not going to do anything for step 4. That was the fix from the control unit. Nothing happens in step 4 on an input instruction or input operation. Only on step 5, we will have the value excuse me, that's in the IO, which is hex DD, being presented to the GPR, right? It's an input. It's coming into a GPR. And now nothing in step 6, and then the IO operation for output only has a step 4 and no step 5 and 6. But we're doing the opposite. We're going from a GPR and we're outputting it to the IO, so it's the value of FF shows up at IO. And at this point now, all of the modules have been independently verified. And the next thing to do is to put all those modules together into one processor module. You can see the CPU module hierarchy over here. And let me take you to the code. Alright, just really quickly, I'll cover this code a little bit. It is going to change when the test circuit comes, but I'll cover all that. And then As for now, I'll take all the modules that I have created, and they will all be in the GitHub space so that you can grab this processor and try and do what you want with it before I'll show you what I'm going to do with it in the next video. And I'll cover a little bit. I'll give you a preview of what's to come in a minute. But here's the CPU. It has an input clock, a reset, that in-out interface, and then the output, the I/O signals going to the other system module as outputs. Just a bunch of internal wires to and from places, and then just connecting all the modules. We got the RAM module here, ALU, the control unit, the TMP, bus 1, the data bus, the GPR file, IR, IAR, ACC, flags reg, and the I/O. And here's a preview of part 6. So, okay, great. We've built a module. Now, we need to make sure it works. So how do we go about testing that and make sure it works? So this is my thought process and my test plan. So when I look at the CPU, what does it do? It processes instructions from memory. So we need to put some instructions in the memory for the CPU to process, and then let the CPU run for the duration of time it needs to process those instructions, and then look at all the control signals and verify that the CPU operated correctly while processing those instructions. So where are these instructions going to come from? And now during my testing plan, my plan is so we can write a test program in the CPU's assembly language, use an assembler program to assemble the test program into binary machine code, and then take that binary machine code and convert that into a Verilog ROM using another piece of software that I've already written in Python, and it works, and then test the program. We'll put all those instructions in a ROM. Then that ROM will be included into a CPU initialization circuit that will hold the CPU at reset while it just accesses signals within the CPU. So the CPU signals are going to have to be, there's going to have to be some more input output for the purpose of taking the instructions that are in the ROM and putting them into the CPU's RAM, then releasing the CPU from reset, allowing it to process those instructions that were just put in RAM. So I already have the assembler program. It was written by my professor. It works great. Like I said, I've written the program to take the .bin and put it into a Python file. I've already started designing, or not a Python file, but a Verilog ROM. And then I've also started designing the CPU initialization circuit. So stay tuned for that one in part 6. Thanks for watching this one. Have a good day.